Okay, hopefully you worked on these problems before you found my answer key video. So I'm assuming you did, so let's look at number 1. Number 1 is asking us to find the secant of this angle, and it's supposed to equal -2. Well, first and foremost, do we usually like to deal with secant? No, we usually like to deal with cosine and sine and tangent. Those are the 3 we work with most often, not their reciprocals. So that's a key word, isn't it? Reciprocal. So secant's the reciprocal of what? Yes, it's the reciprocal of cosine. So the cosine of this angle, I know the secant of that angle is -2, which means the cosine of the angle would be a -1/2, the reciprocal. Okay, a lot better. I like that answer a lot better. But remember, you're still solving a trig function, which means a trig function needs to be by itself on one side of the equal to sign. Is it? Yeah, it's by itself on the left side. And the cosine of this angle is supposed to be a -1/2. Well, the 1/2 tips me off that I'm dealing with a 30, 60, 90 triangle. Agreed? And I need to remember how to draw it, just like I mentioned in the lecture video. This is something that's going to be extremely handy for you to remember how to draw. So, cosine, adjacent over hypotenuse. So adjacent over hypotenuse, which angle that when I do adjacent over hypotenuse is going to give me a 1/2? Yeah, 60 degrees. So I have a reference angle, and the reference angle is 60 degrees. And in radians, it's pi/3. My restriction's in radians, so I need to deal with radians. But since it's a -1/2, and cosine refers to x or y, x, so x is negative in which quadrants? Good, quadrant 2 and quadrant 3. Well done. All right, now, if the reference angle is pi/3, what's the angle in quadrant 2? 2 pi/3. Good, I heard you. And if the reference angle is pi/3, what's the angle in quadrant 3? Good, 4 pi/3. Excellent. But we have this little bit of a challenge going on, don't we? Yeah. We have got this 3/2 in front of the theta, don't we? We have this 3/2, don't we? That makes it a little bit different. And do you remember how we compensate for that? Yes, we have to add 2 pi, which is 1 rotation around the circle, and k tells me how many times around the circle I'm going to be able to go. Because remember, this 3/2 in front of theta ultimately affects the restriction. So we have this 3/2, and we have to compensate by adding 2 pi k. With me? Okay. So let's see what happens. To get rid of this 3/2, multiply by its reciprocal on both sides. So let's see what we get. We end up with theta equals 4 pi/9. And here, yeah, put that over 1. You got 4 pi k/3. Okay. What about here? Same thing. Good. You're going to have to multiply both sides by the 2/3. And when you do that, what remains? Good. On the left side is just theta. Over here, 8 pi/9 plus 4 pi k/3. Good. Excellent. Well done. Are we okay so far? All right. Remember, when it's not a 1 in front of theta, this is the compensation because it's going to change the restriction in the initial phase, shall I say. Good? Okay. Now, k represents the number of times you're going around the circle. So, if k equals 1, all right, How about k equals 0? Okay. So when k equals 0, theta is equal to 4 pi over 9. That's under 2 pi, because remember, I'm solving for theta. That's under the 2 pi, so we're good with that. So let me try another rotation around the circle. That means you're going to take theta equals 4 pi over 9 and add 4 pi over 3. All right, you need that common denominator, don't you? 9. That makes this fraction, if you multiply top and bottom, that makes it 12 pi over 9, doesn't it? So it looks like we get 16 pi over 9. Is that still under 2 pi? Yes, it is. Gratefully, it is. Just barely, but it is. Because if this was 18, now we would have a challenge. All right, let's go with k equals 2. That means I would take 4 pi over 9 and add what? 8 pi over 3? Yeah, I don't think that's going to work, do you? Because if I get a common denominator, that would be 4 pi over 9 plus 24 pi over 9. That's 28 pi over 9. Yet that's not working. So we're going to stop here. We're going to stop with 4 pi over 9 and 16 pi over 9. Cool? Okay. Let's go to this side. How about if k equals 0? Theta is going to equal what? Good. 8 pi over 9. Well, that's under 2 pi, so we're okay. How about k equals 1? You're going to have theta equals 8 pi over 9 plus 4 pi over 3. Okay, we need that common denominator again, don't we? So this would be 8 pi over 9 plus 12 pi over 9, which is 20 pi over 9. And that's over 2, isn't it? This doesn't work. So in this particular case, your theta is going to equal 4 pi over 9, 16 pi over 9, and 8 pi over 9. 2 from quadrant 1 and only, 2 from quadrant 2 and only 1 from quadrant 3. Good? Okay. Example number 2, coming your way. Okay, here's problem number 2. Did you get it already? If you did, scoot to problem number 3. All right? Okay, but I'm going to go with problem number 2 here in the meantime. So I'm dealing with a trig function. I need to make sure the trig function is by itself when I'm solving a trig function equation. Gratefully, sine is by itself and it's equal to 1. Got it. Okay, so the answer of 1, it's not on the 30, 60, 90 triangle by itself. You always have 1 in a fraction, don't you? Like 1 over 2, right? The 45, 45, 90 degree triangle, you're like, it has 1s. That's true, it has 1s. But the only time you would get an answer of 1 on that triangle is if you took the tangent, because then it'd be 1 over 1, which is 1. All right, which leaves me with the unit circle. Anytime I see an answer of 1s or 0s, my brain's always going to go immediately to that unit circle. And that unit circle has a bunch of 1s and 0s on it. Because remember, when you look at the coordinates, right, you look at the points at each location, there are a bunch of 1s and 0s. So if I'm talking about the sine of an angle and it equals 1, sine, yeah, that's the y's. So where are the y's of 1? Here only, correct? So in that case, your angle, right, your theta is going to be 90 degrees or pi over 2. Since we're in radians, we have to deal with pi over 2, don't we? All right, but there's that 3 in front of it, isn't there? Ah, yes, we have to compensate, which means 3 theta is not just equal to pi over 2, It's equal to pi over 2 plus 2 pi k. How many times around the circle can I go and still have theta remain in that restriction? Basically, that's what you're trying to find out. Cool? Okay, need to get rid of that 3. What are you going to do? Divide by 3. Got it. Divide by 3. This is basically multiplied by a third, isn't it? When you divide by 3. So, theta equals pi over 6 plus 2 pi k over 3. Now, some of you may be going, wait, isn't that a reference angle? You know, what's actually on a boundary line, there's really no reference angle because it's one of the 4 of these. The only time it could be 2 of them is, say, your cosine is 0 or your sine is 0. Other than that, there's really no reference angle when you're actually on one of the axes. Good? Okay, so here we go. We are going to allow k to be equal to 0. And when k is equal to 0, we just get pi over 6, don't we? Cool. That's under the 2 pi. We're still good. How about k equals 1? Well, you'd have to have pi over 6 and add 2 pi over 3. Okay, common denominator. Yeah, that'll be 4 pi over 6, won't it? Which, when you add it, will give you 5 pi over 6. All right, still good there. No problem. How about k equals 2? Well, that would be pi over 6 plus, if k is 2, 4 pi over 3. Yep, need that common denominator again, don't we? So that's 8 pi over 6. What do we get? 9 pi over 6. Oh, wait, that reduces. 3 pi over 2. Excellent. Still under 2 pi. We're good. I'm running out of board space. Let me try 3. I think I'm pushing my luck. Pi over 6 plus 2 pi times 3 over 3. Yeah, this is going to be 2 pi. You're already going to be over 2 pi. So in this particular case, since there was a 3 in front of the theta, that's a hint that I'm going to go 3 times around the circle, which is why I literally have 3 answers here. I have pi over 6, I have 5 pi over 6, and I have 3 pi over 6. Over 2. Sometimes you can predict how many solutions you're going to come up with. And in this case, I got 3. In the first one, but there was a 2 theta, I actually had 2 from each quadrant. So I got that. The 3 over 2, that's 1.5, isn't it? That's kind of iffy. Anyway, I have one more example for you. So example number 3, coming your way. Okay, last problem. Did you get it? You're like, this one was a little bit different. It was a little bit different. Why? Because I have 2 different trig functions. I have cosine and sine. And I'm like, well, what am I supposed to do with that? Well, let's talk things through a little bit. You know, whenever I see a trig function squared, my brain goes immediately to Pythagorean's theorem and might try a substitution. But the real key for me here is this cosine is of a double angle. And this sine is a single angle, a 1 theta. I would rather deal with a 1 theta because I don't have to do that plus 2 pi k to compensate for the coefficient in front of theta. If I can make this into a 1 theta, my life is going to be so much nicer. So, if you look at the double angle identities for cosine, you've got like 3 choices. You're like, which one do I choose? Think about it. Your other trig function is sine squared. So which one would you choose? Pause the video, I'll wait. Go find out which one. Did you get it? Good, so did I. This is what I chose. I chose to substitute in 1 minus 2 sine squared theta. Do you know why I chose to do that? Yeah, because the rest of the equation says plus 10 sine squared theta. Now I've got nothing but sine squared thetas in the equation, which is going to make this so nice for us. Watch. What are you going to do? Collect like terms. So I end up with 1 plus 8 sine squared theta equals 7. Stay focused. Right, you've got to get the trig function by itself, so move the 1 over. And then you've got to move the 8, right? Because you need the trig function by itself. Well, gratefully 6 over 8 reduces, doesn't it? What does it reduce to? Yeah, 3 over 4. Got it. But the trig function is not quite by itself. Yeah, you got to get rid of the square. So take the square root of both sides. Good, excellent. And when you take the square root, how many answers are you going to get? Excellent, 2 answers, because the square means you're supposed to have 2 answers here. So you're going to end up with the sine of theta equaling a positive square root of 3 over 2, right? And you're going to end up with the sine of theta equaling a negative square root of 3 over 2, aren't you? All right. So I am going to bring my work up here. And before I do that, my brain is seeing square root of 3 over 2, which tells me I need to look at what? The 45, 45, 90 triangle, the 30, 60, 90 triangle, or just the unit circle? Good, the 30, 60, 90 triangle. So let me draw that over here. So 30 degrees, 60 degrees. Remember how to label it. And I'm talking sine. Sine is opposite over hypotenuse. So the sine of 60 will give me square root of 3 over 2, won't it? Good. And so that tells me my reference angle is 60 degrees. But in radians, because that's what we're talking about, it is pi over 3. On both of these, right? The reference angle is 60 degrees or pi over 3. Agreed? Okay. Now, we got to figure out quadrants. I'm going to bring my work up here because I'm running out of board space down there. So the sine of theta is a positive square root of 3 over 2. My reference angle is pi over 3. So, which quadrants have a positive sign first and foremost? Quadrant 1, quadrant 2. Got it. So in quadrant 1, reference angle is pi over 3. Pi over 3. Quadrant 2, my reference angle is pi over 3. So what's that? 2 pi over 3. Let's look at the other one. The sine of theta is equal to a negative square root of 3 over 2. Sine is negative in quadrants. Good. 3 and 4. So in quadrant 3, knowing your reference angle is pi over 3, good, that's 4 pi over 3. And in quadrant 4, that's 5 pi over 3. Excellent. Now, let me ask you something. When we solved, this was where we were at, right? We took the square root of both sides, and I came up with these 2 answers, or these 2 little equations. Do you notice this theta? Both of them? What's the coefficient in front of both of these thetas? Yeah, it's just a 1, isn't it? Because it's already a single angle, I don't have anything else to do after this step. This is it. This is done. This is what we're used to working with. Those first 2 problems in this answer key video, they had a coefficient that was not a 1 in front of theta, which made me compensate and put the 2 pi k But since both of these equations had just a 1, an imaginary 1, in front of your theta, when we get to this point, when we got the quadrants, we're done, just like we're used to. Good? Cool. Okay, hopefully this answer key video made sense to you. Hopefully the work makes sense to you. If you need to go back and rewind it and listen to it again, then please, by all means, do so. Yeah, otherwise, I'll catch you on the flip side.